Okay, hey guys, it's day 11 homework technically, but I think I said that I'd go over these few problems in case anyone wanted to know how. These are from the classwork. There aren't any homework questions on these, and we didn't put them on the quiz either. So you could definitely skip this without any detrimental effects on your grade. However, you might want to listen in and learn. Um, so how do you do this? There's me. Okay. One way to do this, since they're exponentials, is to go ahead and use logs. Now, you've got a base 3 and a base 4, so there's no way to express these with a common base, but that's sort of fine. We could still take the log of both sides. And one thing to do is maybe use one of the bases as the base of your log. So, oh, that's too thick. You could go with a log base 3, let's say. You get log base 3 of 3 to the 2 minus 3x. And that would then be equal to the log base 3 of 4 to the 2x plus 1. Okay. So now, because we took the log base 3 of 3 to this power, the log base 3 and the 3 will cancel, and you'll just get back that power. So you get 2 minus 3x. So at least that side cleans up nicely. On this side, you can use power rule to pull out the 2x plus 1. But then you'll still be multiplying by the log base 3 of 4, which does not evaluate cleanly. So now you've got essentially this ugly value. But that value is just a constant. And so imagining for a second that this was just like a 7, you would distribute in the 7 and solve from there. And that's exactly what we have to do now with this. We just have to treat it like any other constant. So I've got a 2 minus a 3x. And if I distribute this in, then I basically get 2 times the log base 3 of 4 as a coefficient on x. Yeah, I guess that's the best way to write that. Plus log base 3 of 4. Okay. So now get your x terms together. I would add the 3x to both sides. That means the log base 3 of 4, which is a constant, I would subtract from both sides. So I basically now have 2 minus the log base 3 of 4. And that's equal to 2 times the log base 3 of 4 minus 3x. Ooh, I forgot the x on this. That's a big deal. So this has an x. And then we're also subtracting 3x. And then where the heck do we go from here? Well, it's not a heck of a lot that we can do. Not a heck of a lot. 2 minus log base 3 of 4. We can't really change that. And what we can do here really is just factor out the x to have x times 2 times the log base 3 of 4 minus 3. And then we can just divide by that whole mess to get x alone. So I'm getting an answer of 2 minus the log base 3 of 4 all divided by 2 times the log base 3 of 4 minus 3. And that's x. So that's the answer. That's right, but it's pretty ugly. So the question is, like, would you bother trying to clean that up? And sure, let's just talk about how you could clean it up. In the numerator, that 2 could be expressed as a log base 3 of 9. In the denominator, you'd pull in the 2 as a power. So you'd have log base 3 of 16. And that 3 would be a log base 3 of 27. Okay, that certainly doesn't feel better. But now we can use quotient rule to get to log base 3 of 9/4 all over log base 3 of 16/27. Okay, that doesn't feel much better until you realize that now you could use change of base formula in reverse. You've got a common base 3, common base 3. So the denominator could be the base of your log. You could go log base 16/27 of 9/4. And that as an answer doesn't feel awful. I mean, it's terrible, but it's not awful. I would say that this answer over here in gray is worse. So, you know, whatever. Before I really say that I nailed this, I'm going to pull out the calculator and even just make sure I'm even right. But I think I am. Hold on a second. All right. So, yeah, I checked it out. I'm happy to report that they are, in fact, equivalent to one another. Again, you never have to do this, so it doesn't really matter how you give me your answer because you'll never be giving me this answer. You know, there's a case to be made for this form to have nice simple logs with bases and arguments that are whole numbers. But there's something to be said for this form as well, to just have a single log expression rather than a big, you know, rational expression with binomials in the numerator and denominator. I mean, that thing is big, whereas this thing is compact. So whatever. Anyway, look, they're the same, like I promised. Moving on. Oh, yeah, right. By the way, this was not the best way to do this problem. There's a better way. So I'll do number 2 the better way. How will I do it the better way? I'll duplicate this page. And better is debatable, of course. Everything's debatable. So maybe I'm going to do this some other way, and you're going to say, no, Mr. F, that's worse. But I don't think so. I think it's better. Fit to width. So sure. Property of proportions. I don't even know what that is. Appearance of the calculator. All right, anyway, the other method I was going to use actually is right here in the instructions, which says solve using natural logs. So that was to be my advice, was just we would use natural logs here. I'm going to get rid of this. Give myself more room to work. So on one side of the equation, I mean on number 1, we took the log base 3 of both sides just because it was convenient to at least have one side come out nice. But this time I'm going to say, you know what, forget that. I don't care if either side comes out nice. I'm going to just use a nice ln because that's simple. So it'd be ln of 12 to the x minus 4. It would be the ln of 4 to the 2 minus x. And then what happens from here is, well, you can use power rule on both of these. So you get x minus 4 as a coefficient on the ln of 12. Here you get the 2 minus x as a coefficient on the ln of 4. And in both cases now, the ln's would want to distribute in. Is there any way around that? Nah, not really. So you basically get x ln 12 minus 4 ln 12. It equals 2 ln 4 minus x ln 4. Okay, and now from here, it kind of goes the same way as the previous problem. You've got an x term here and an x term here. You're going to want to pull those together onto one side of your equation. You've got a constant and a constant. You'll push them to the other side of the equation. Now, in what order do we do that? It shouldn't matter, but let's think it through. I suppose if ln of 4 is less than ln 12, then we probably want to be pulling that guy over to here. So you'll have x ln 12. Oh, we're adding anyway, so who really cares? It's going to be positive result no matter what. So x ln of 4, it equals 2 ln of 4's plus 4, plus 4 ln of 12's. Okay, factor out the x like you did before. ln 12 plus ln 4. Is there anything I can do here that's worthwhile? I could factor out a 2. Is that worthwhile? I could simplify these expressions. Is that worthwhile? I'm going to say no. At least not for now. I don't care. I just want to arrive at an answer. Once we have an answer, we can clean it up if you want. By the way, we have an answer because you can now divide by the ln's. Now it's going to be another ugly answer that could certainly be cleaned up, but it's going to be x equals 2 ln 4 plus 4 ln 12 all over ln 12 plus ln 4. That's it. I mean, technically you could stop there, right? That is an answer. That is something we could plug into our calculator and evaluate. It's probably tempting to try to cancel stuff. You've got an ln4 and an ln4, ln12, ln12. But remember, you cannot cancel like that. You know, if you have a plus b, you know, we kind of have like an a plus b over a b plus a or something. You just can't cancel the a's though. It's because you can't cancel terms. You can only cancel factors, which I've said a bunch of times. And hopefully it's starting to make sense. Just things that are connected to other terms with plus signs or minus signs, you just can't cancel them. You have to be able to factor them out first. And then if they factor out, then by all means cancel them, but these don't. So you can't. Yeah, you just can't. Sorry, man, you can't. Should we talk about simplifying? I don't wanna. Let's not waste too much time. I will say though, 12 is 4 times 3, right? So we could split this at least to some ln's of 4 and some ln's of 3, and then we could combine the ln's of 4 so that instead of having a 12, we'd have 4's and 3's. 4 is 2 squared. So there is kind of a lot of simplification to do here. You know what? As an exercise, I'm gonna do it. And you guys can watch and follow along if you want. If you want to be good little calculus students next year, then it wouldn't kill you to really sort of follow along with this. But you really don't need it. So what am I saying? I'm saying that this is 2 ln's of 4. This 4 ln of 12 is really 4 ln's of 4 plus ln's of 3. So I have 4 ln 4's plus 4 ln 3's. So these will combine to just become 6 ln's of 4. And so there's some value in doing that. So this also is an ln of 4 plus an ln of 3 plus an ln of 4. So again, you've got a bunch of ln of 4's that can be combined. Those will combine, those will combine, those will combine. So that is a simplification, you know, not a great one, but it does make the argument smaller. So we now have 6 ln 4 plus 4 ln 3 all over 2 ln 4 plus 1 ln 3. All right, now I'm saying we can do even better than that because 4 is actually 2 squared. So then we can use power rule, pull out the 2, and get 12 ln's of 2. So we now have 12 ln's of 2 plus 4 ln's of 3 all over. This will be the same deal. If this goes to 2 to the 2, then I pull out a 2, and 2 times 2 makes 4 ln's of 2 plus an ln of 3. And I had hoped we could do more, but we can't. We could factor a 4 out from here, but then you'd be too tempted to cancel it with that 4, and you can't because this guy doesn't have a 4. So maybe I'll factor it out anyway though. So 4 times 3 ln's of 2 plus a single ln of 3 all over 4 ln 2 plus an ln of 3. In terms of just breaking it down that way, this would be the best you could do. Could I though? I could combine all these things into super logs and do change of base formula like we did before. So I'm gonna do that too, just because I don't know, let's get wild and crazy. All right, so the easiest way to do that would be skip this and pull in your power, pull in your power. It's product rule. So your numerator would be 1 super log of 2 to the 12 multiplied by 3 to the 4th. Should be some giant monster number. In the denominator, you'll have super ln of 2 to the 4 times 3. So now, I don't know. I'm thinking there's probably a way to clean this up, but maybe I just don't know. These two ln's obviously both have bases of e, so we could now apply the change of base formula in reverse to have the log base 2 to the 4 times 3 of 2 to the 12th times 3 to the 4th. You know, so that answer is clearly worse than other answers because these denominators are gigantic values. This argument is a gigantic value. I don't think that there's a great way to clean this up. So I would just say that this answer is bad. This answer in blue is fine. And I think for our purposes, just this answer in gray was okay. I don't know. Probably the blue one's best. Anyway, I don't care anymore. Hopefully you guys feel comfortable working with this kind of equation. And by this kind of equation, I mean an exponential set equal to another exponential where the bases are different and cannot be expressed with a common base. You've got your two options, which is just take the ln of both sides or any log with any base. Over here, we chose to do a log base 3, knowing that the left-hand side would simplify nicely and would only have to deal with the right. Over here, we used a natural log just so that we always had the same base of a log. It was all ln's, and so we knew that we could work with that fairly easily. That's about it. I think I'm choosing not to bother doing number 3. So I'm just not gonna. Y'all can do it and see what you see. Okay, so now we want to talk about Newton's law of cooling, which is just a formula. It's basically like science class now. If you know what all those variables mean, then the math isn't too bad. I can certainly walk you through it. I wanted to come to this page. These are the class notes. I'm sure you all were paying very close attention, but just to go over everything one more time, on the quiz, I will give you the formula. I will not give you the explanation of what every little variable represents, of course. That much, I think it's fair for me to ask you to know. So T of T, that's the Y value. That's our Y value. That's the temperature after some amount of time has gone by. So if you wanted to find the temperature after 10 minutes, then you're looking for T of 10. Then TA, that's the ambient temperature. Ambient means the surroundings, which typically means the air, right? You just set something on a table and it cools down, so it's the surrounding air. But you could dunk something into a bowl of ice water, and then it's the temperature of the water. You could drop something into oil. You know, blacksmiths do that when they're trying to temper metal. They put it into hot oil and it cools down. So the temperature of the oil would be the temperature of the medium. In fact, that's how I've seen it before, I think, was these were T sub M's for medium. The surrounding medium was air, water, oil, whatever, snow. If you drop something into snow, I don't know. Anyway, that's what it is. It's the temperature of the surroundings. T sub 0. Well, you could say that. First of all, just how do you even say it? You could say T0. You can say T sub 0. You could say initial temperature, because we know sub 0 always represents the time or the temperature literally at time 0, meaning the initial time. But what I tend to say, and if you hear me say it, you'll know what the heck I'm talking about. T sub 0 is T naught, right? Not meaning nothing. Like all my valiant efforts were for naught. So T naught is commonly used everywhere other than the United States. In class, I think I was saying, they say it over in England. But, England had a pretty wide reaching influence. So a lot of other places say T naught as well. I don't know. It's what my teachers in high school said. So I keep on saying it, T naught. Oh, look, it's TA. That's the same TA from over there. E is E. It's the number 2.718. K is a decay constant, and that's the tricky bit about these problems is you have to actually solve for your own value of K. And we had a similar thing going on before. Even back when I'm going to just write, oh no, this corner, you can't see anything I write in this corner. Look, I'm writing, see, but you can't see it because it's behind the little image of me. So let me write over here. For a while, we were just trying to write exponential models, and we had to solve for the base before we could do anything. And well, that's the same deal. You had to be given data points so you could find B, and then once you had B, you could do more with it. We had to find A too, but that was easier. Anyway, we got to solve for K, and to solve for K, technically you need 2 data points, but typically they hand you the initial value on a silver platter, and then they give you some other time and temperature, and then you can substitute it and solve. So K is just some constant that's going to vary from problem to problem because, a meteor that strikes the Earth is going to cool at a different rate from, a block of ice that you just set out on the kitchen table. And so everything has different properties. And so the K varies from problem to problem to address that. Am I done talking? I'm done talking. All right. I'm going to want to take this formula with me because I'm going to forget it. I know I'm going to forget it. Bonk. Zoop. Bonk. All right. So I'm not going to rehash the homework, the classwork problems, although I should probably rehash this crime scene one because we never actually finished it, but I'm not gonna. Although the third homework assignment is a lot like this. When I do the third homework assignment, I may pop back and revisit this. So if people feel like they want it, maybe I'll do it. How about that? You get a maybe. All right, hey, look, it's the homework. And right away, I've got a mea culpa. Look at how I cropped it. I cropped it to how long will the, and then I left the actual endpoint off. Nobody has emailed me about this yet, I don't think, which is a little disheartening. Usually a lot of you guys get right on your homework. Anyway, look, we can just line this up like that. Perfect. And there you go. We're trying to find out when the cup cools to 30 there. And you can even see the answer. I hope you got 28.41. Let's do this problem. I will paste our little formula. There it is. And again, I don't mind showing you the formula. Like I told you before, it will be on the quiz, so don't even worry about memorizing it. Here's what you got to do. You read the problem and you identify all your variables. It says a cup of coffee has cooled from 92 degrees Celsius. That's them telling us that T naught is 92. Why? Never use that. So T naught, the initial temperature, is the 92 degrees to 50 after 12 minutes. 50 after 12 minutes is really like an ordered pair. I'm telling you, when X is 12, Y is 50. So that's basically a time associated with a temperature over time. It says in a room that's 22 degrees Celsius. That's the temperature surrounding the thing. So that's the ambient temperature or the temperature of the medium, 22 degrees. So how long will it take the cup to cool to 30 degrees? Well, that is a second order pair where you know the temperature, but you don't know the time. So before we can ever get to that, we need to figure out K. So we got to first use all the green given information to find K. Then we can update our model with the right value of K. And then we can just plug 30 in for T of T and solve for the associated time. Those are the steps. Let's do them now. So like I said, we know that the temperature will be 50 when 12 minutes have gone by. We know that the ambient temperature is 22. We know that the initial temperature is 92. We know that easy. We're wondering about K. He's the only variable that should be left when we're done. And we actually know the associated time with the 50-degree temperature is 12. So there you go. You have all the information except for K. So now you just solve. I'll try to go through this sort of faster than I normally do. You'll subtract 22 from both sides to be left with 28. You'll take away 22 from 92 to be left with 70. E to the negative 12K. If you divide by 70, you'll get 28 over 70. Sure, that is a decimal, sure, but you don't want to use decimals because when you use decimals and round them off too aggressively, the result can be a massive loss in accuracy. If you are off by a couple decimal places and then you go to take a logarithm, you can end up off by 10 whole unit values, like it's a big deal. So don't make this a decimal. Instead, just simplify. I can chop these both in half and get 14/35. Oh no, that's not the best I can do. I can divide by 7 now and just get 2/5. Yeah, so 2/5 is nice. And guess what? You're lucky. Since 2/5 is exactly 0.4, you may use that decimal if you really want to, because there's no loss of precision. 2/5 really does equal exactly 4. Now, if this was 2/7, you'd be talking about a decimal approximation that extends forever. Not forever, but it extends ugly, and you would likely round it off more aggressively than you ought to. So I'd rather you just got into the habit of leaving your fractions in reduced form and working with them as they are. Hey, guess what? That equals e to the negative 12k. So the only thing left to do now is take the ln of both sides. So you get the ln of 2/5. And that would equal, I guess I'll take this part slow. It'll technically be the ln of e to the negative 12k. And you got two ways to think about it. If you get the whole deal about taking a log whose base is equal to the base of an exponential, so they just cancel and you get your power, then great, think of it like that. That is what's happening here. A log base e and an exponential with a base of e are inverses of one another, so they do just cancel and you'd just be left with the exponent. Sort of a justification of that is we apply the power rule and out pops the 12k multiplied by the ln of e. But ln of e is log base e of e, so of course its value is 1. And since multiplying by 1 does nothing, we essentially see the 1 just go away. And so we see that there is a clear line from here to just having the power. These are the steps that technically happen, but skip those steps from now on because there's just no reason to show them. 2/5. All right, now what? Get rid of the 12 by dividing by 12. Except no, Mr. F doesn't like that. Mr. F prefers multiplying through by 1/12 and a negative. We want to kill the negative too. So we end up with a coefficient of negative 1/12 on the ln of 2/5, and that's our k. Yoink. So as I explained in class, the way this will actually appear on your quiz is you'll just be filling in some field with the value of k. So you'll have to know how to evaluate that. And it's not hard. You literally just do it in your calculator. And any calculator can do ln. So you'll be fine. I've lost myself. Oh, I want to go here. Yeah, here. All right, here's your calculator. So I think I just told you that I wanted negative 1/12. I think that's got to be in parentheses. All right, so I wanted negative 1/12 of the log, natural log of 2/5. All right, when you type your answer in, I demand you give me 4 places after the decimal. So you're rounding off between the 3 and the 5. 5 is equal to 5. You know that anything 5 or more, you got to round up. So I'm looking for 0764. Anything else will be marked wrong. 0764. So you'll say k is approximately 0.0764. There's your k value. Now don't use that in your model. I still want you to use the real deal in your model. This is still rounded off and it'll cause your follow-up answers to be wrong. This is just what you're coding into the computer. Okay, moving on. We have our k. So now what? We plug it into our equation. Paste. Of course, it got pasted up here again. Of course, it got pasted nowhere. There it is. Okay. Running. Sure. No. I don't remember any of this info anymore. And this is ludicrously oversized. All right, so what's our model? Well, T of T is our Y variable, so we're not plugging anything in for that just yet. The ambient temp was 22. I don't know, I gotta look. 22, I'm gonna start trusting myself. 22 plus the initial temperature was 96. That's why we had a base, oh no, 92. That's why we had a base of 70, right? 92, take away 22, multiply by e to the, all right, again, I reiterated this in class, but I'm reiterating it again. Notice the equation already has a negative built into it. The value of k also has a negative built into it. That means when I substitute in, I'm gonna get negative, negative 12, blah, 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 blah. The negatives cancel. So go ahead and just let that negative cancel. You get 1/12 times the ln of 2/5 times, oh, nothing. Oh yeah, times t, times t. Okay, I knew there was three things. Ay, ay, ay. Hey, there's our equation, but it's garbage. Let's clean it up. The T of T is fine. 22 is fine. Well, you know what? The 22 is not fine. You guys would probably prefer to see it at the end. That's typically how our exponential equations look. So I'm going to ship that bad boy to the end. This is 70. Go ahead and do that math. There's no reason not to. So we now have 70. This is an e to the power of all this junk. But we remember, I think, that if you have an exponential base to the power of m times n, lmn o p q, I don't even care. This resulted from having a power to a power. That's when you multiply powers. So you could pull any of those powers out. If you wanted to pull out just the n, go ahead. That would be fine. This is power to a power. You're multiplying the n back in and you're back to normal. You could pull out a couple of them, b to the mq, but I'll put the p and the n together on the outside. That's fine too. You're sort of allowed to do that. So armed with that knowledge, I would love to leave the ln in, actually. I'd pull out the t and the 1/12. Why would I leave in the ln? Well, because again, e to the power of the log base e, that has that inverse relationship. So e to the ln of 2/5 is just going to be 2/5. Now with the 1/12 and the t wrapped in there, it doesn't work. You can't cancel that out quite the same way. Now you could pull the 1/12 in as a power, but then suddenly you'd have a base that's 2/5 to the 1/12, which is an ugly base. So our best bet by far is to leave the ln expression in, pull out the t and the 1/12. And of course, for those of you paying attention, 1/12 times t, that's just t over 12, right? So this will go to t over 12. Don't forget your 22 plus 22. We're sticking it on the end. Okay, so now, as I said, e to the ln of 2/5 is just 2/5. So our little equation boils down to actually a fairly clean exponential with a base of 2/5. All the logs are gone. T over 12 plus 22. There's our model governing the temperature of this cup of coffee. It's not bad. And we were trying to figure out when it cools down to 30. All right, fine. So you plug in 30 for T of T and you solve for T. And that math won't be bad. N goes to 30. It equals 70 times 2/5 to the T over 12 plus 22. You're going to want to get rid of the 22. So subtract it. I think that makes 8. You're going to want to get rid of the 70. So divide it. I think that makes 8/70ths. You're going to want to reduce your fractions. Chop those in half. 4/35. Can't do any better than that. 4 is a 2 and a 2. 35 is a 5 and a 7. Nothing cancels. So we're as good as we're going to get. That is equal to a base of 2/5 to the power of t over 12. All right. Pretty sure I'm sitting firmly in exponential town, and I don't know what to do from here. So just get it into logarithmic form by converting. If you sort of understand how to convert, you just convert. I still prefer to just think of it as taking the log of both sides. My exponential has a base of 2/5, so I'll take a log with a base of 2/5. So I'll get log base 2/5 of 4/35. And again, technically that'll be equal to the log base 2/5 of 2/5 to the t over 12. This is a step you should never show. You should know by now that, the act of taking the log base 2/5, the whole point of that was to get the log to cancel with the exponential and just give us the power. So for sure, just go directly to the t over 12 equals the log base 2/5 of 4/35. And hey, guess what? Just multiply by 12 and you're done. So when you multiply through by 12, you get a final answer of 12 times the log base 2/5 of 4/35. And when you distribute over here, of course, it cancels to give you t. So there's your final answer. It's not very pretty, and you can't enter it into your computer. So what are we doing instead? We said we're going to evaluate it, and we're going to round it to the nearest minute and plug that into the computer. So when you take the quiz, you'll see a little field, and I'm making it super clear what I'm asking for. It's going to say t equals big dumb box that you can type into, and I'm pretty sure right underneath it, I literally wrote round to the nearest minute. So you'll know what to do. You can't screw it up. So how do you evaluate this though? Let's find out in a second. Okay, I'm back. What are we doing? We're evaluating this thing. All right, and as I've explained a billion times, as long as you have a new calculator, pretty new, you'll be able to enter, what did we say the keystrokes were? Math, and then alpha. And then you just hit math again. And technically when you hit that, you're not really hitting math, you're hitting the alpha is the green button, right? So when you hit math again, you're actually hitting the option for the letter A. You're choosing option A from the math menu. That's what's actually happening here, just so you guys know. It's not some weird shortcut like Control V. You're actually just doing things. I hate when teachers tell you, they're like, oh, you hit math, alpha, math, and you don't know what it is, but you're just working the menu. You hit the math menu, and then the option you want is way down on the list. It goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it starts over again, A, B, C, and the option you want is option A. So when you do that, you will get a prompt that says log with a little dotted square of a bigger dotted square. And you will then have the freedom to enter in whatever the hell you want. So that's great. If that works for you, wonderful. It doesn't work for me, and my calculator is not that old, as I've explained before. I've got the whole TI-84 plus silver edition, but it doesn't work. It's a little too new of a feature even for that. So what do you do if you don't have that? You would have to use change of base formula. So no big deal. You just would have 12, and you'd change your base probably just to ln. You could do log. You could just do plain old log base 10. But ln has fewer letters. It has 2 instead of 3. So I like to use ln. But you would do the ln of 4/35. And you'll still get the right answer as long as you divide by the ln of the old base, 2/5, 2/35. So I'm just going to do it both ways so everybody can see it. So if I go back to my calculator, clear all this garbage. So the easy way, again, remember, is you hit math, and then you want option 0. So you hit, oh my God, you want option A. So you hit alpha A, math, alpha, math. Of course, I forget already. It's nearly impossible to remember these numbers. All right, 4/35, 2/5. Got it, and a 12. Take me back. There it is. I'm still sharing that, right? New share. Yeah, all right. So the argument is 4/35. The base is 2/5. The argument is 4/35. 35th. Okay, and I forgot my 12, but I can stick the 12 on the end, or I could even hit enter and then do it. But I'm getting 28.406. I believe, we just saw the answer key said the answer was 28.41, so we know we're good. Again, if you had to use change of base formula, then you can just type 12 times the natural log of the 4/35. That's the one that goes in the numerator. You also have to close parentheses. Don't forget. Then you're going to divide by the natural log of the old base, which was 2/5. And I will get the exact same answer. Notice, oh, by the way, you cats may not know this. See right above enter where it says entry? If you hit second enter for entry, then you get your previous entry. So now I can go back and edit that. I just want to prove to you that if you're lazy or sloppy and you miss that close parentheses there, bonk. Oh, you get an error. That's not bad. That's better than getting an answer and thinking you're right when you're actually wrong. So when you get this error, just choose go to, and it doesn't really try to show you. Is it saying just close these end parentheses? No, that's bad too. Okay, good. So hopefully you would figure it out. You would see that you need to put something in. Now, another trick you guys might not know. Hey, look right here where above delete, it says INS. That's for insert. So if you didn't know this, you don't have to retype the whole damn thing. You can hit second insert and then jam a parenthesis in. So when you're in insert mode, it works like Word or Google Docs or whatever works when you're typing. If you forget a word, you can type a word in and it doesn't overwrite, but your calculator overwrites, but not if you hit that button. If you hit second insert, then you can type things in and it pushes the rest over. Pretty handy trick that a lot of math teachers wouldn't teach you, but I love you guys, so I do, because I care. All right, moving on. 28 point, oh, by the way, if you gave me 28.41, you would get marked wrong and get absolutely no credit from the computer. I'd go in and give you partial credit, but I'm asking you to round to the nearest whole number, right? So you're just going to say 28, just 28. Don't give me any decimal places, because I'm specifically asking for the nearest whole number of minutes. I have stopped screen sharing, so I better go back. Bonk. All right, so you're typing in 28 and you're done. Okay, that was one problem. That's probably all you need, but I said I would do all of them, so here I go. This one's about a cake. You can see that it's identical. So the cake's removed from an oven. There's your initial temp. It cools to 120 after 20 minutes. There's your ordered pair, your data point that's going to allow you to solve for K. In a room that's 65 degrees Fahrenheit, there's your ambient temperature, T sub A. How long will the cake take to cool to 90? There's your T of T for the T that you're trying to solve for. So I'm going to run through all these steps again, ideally as fast as I can, see if I can make this quick. Paste is my equation. Shrink it. Remember, the first thing we're doing is solving for K. So just grab all the given info and jam it in. We're 120 after 20 minutes, so that means T of T is 120. T is going to be 20. The ambient temperature is our 65-degree room. The initial temperature is the temperature of the oven, 350. The ambient temperature is still the 65. We're going to multiply by e to the negative k times time. Again, the time has to be the time that's associated with the 120 temp, so the 20 minutes. Yoink. All right. To solve for k, we'll take 65 away. So 55. We'll take 65 away from this, so I despise arithmetic. 350 minus 65, 285. Hey, that was a little bit embarrassing, but okay. This is negative 20k. Okay, divide by 285. These are clearly both divisible by 5. So do that. You'll get 11 over 57. It's an ugly fraction, but it's whatever. It's not that bad. It's better than a rounded off decimal that gets you the wrong answer. This is e to the negative 20k. Like I said, you're now going to take the ln of both sides. So you get ln of 11/57. When you take the ln of this, you just get negative 20k. So divide by the negative 20, or in my preference, multiply by negative a 20th. There's your k. What is that approximately? I don't know. Why, it's 0.823. 0.0823 is what I meant to say, of course. That is not exact. That is rounded off. This would have been an ugly irrational number that goes on forever. So remember, that's not what we're using in our equation. That's just what we're entering onto our quiz. But we're going to use this guy in our actual equation. So let's write that equation now. Bonk, yoink, shrink, move. All right, so now that we know k, we can get down to business. We said, we do know t of t. I'm going to just plug it in now. We want to find the time associated with a temperature of 90 degrees, so plug in 90. 90, bonk. It equals the ambient temperature, which is 65, bonk. Plus the difference of the temperatures, which we already calculated to be 285. So just use that right away. Then you've got e to the negative k. Again, the negative signs will be canceling for us. So you get 1/20th ln of 11/57 times t. So we're here. We did already talk about how this can clean up. So if you've skipped ahead to this problem or whatever, I'm much more thorough in the previous problem. You might want to go back and watch that if there's anything here confusing you. But this will be 285. We're pulling out the t in the 1/20th to give us an exponent of t over 20. So now we're left with just e to the ln of 11/57, and that'll just be 11/57. So we now have a very clean, fairly easy to solve equation. So we just solve it. We're going to want to subtract 65, divide by 285, and then take the log base 11/57 and then multiply by 20. Easy peasy, right? So off I go. If I subtract this, I'll get 25. I'll divide by 285. And I abhor unreduced fractions. So I'm dividing by 5, and I'll get 5/57. Okay, and that'll equal 11/57 to the t over 20. Yoink, yoink. Take the log. You now have the log base 11/57 of 5/57 equals t over 20. So multiply by 20. And you're done. But no, you're not really, because you're actually going to be prompted to find the nearest whole number of minutes. So you do have to evaluate. Let's use this cool rounded off box. Okay, that's not cool. Makes that skinny. Wait, you still look like, oh, right. Okay, hold on, I got this. It's supposed to be blank on the inside, dark gray on the outside, and skinny. Zoop. Okay, you got to fill that box. I'm not showing you. I'm just doing it myself. If you want to know how to enter this in your calculator, I covered it in the previous problem, so rewind. It'll be the ln of 5/57 divided by the ln of 11/57 multiplied by 12. 20, I meant 20. 29.585. So it's approximately 29.585, 1987.6. All right, if we're rounding to the nearest whole number, then the only thing that matters is that 5. He says round up. So t will be approximately 30 years. Done. Okay, another one down. Now, number 3 is the one that is different and has a bit of a trick to it. So let's do that. This one's about a casserole. It says a casserole is removed from the oven and it cools off in a way that the difference between the casserole and the room temperature decreases exponentially with time. So suppose you remove the casserole from the oven and it cools to 200 degrees Fahrenheit after 15 minutes. 10 minutes later, it's 144.83 degrees Fahrenheit, and the temperature of the room is 75 degrees. Write 3 ordered pairs to represent the problem situation. No, I don't know how. Ms. Butler does, though. Oh no, I moved it. What have I done? Too small. All right, Butler, what'd you do? 0 and T. No. I only see 2 ordered pairs, Butler. How are you going to ask for 3 and then only give 2? This counts? This ordered pair that has a variable in it? Right, 3 ordered pairs to represent the problem situation. I guess that's what she means. Okay, sure, fine, Butler, that's what we'll do. Okay, so she's saying for a problem like this, we really need to know that initial temperature. And the problem is we don't. For whatever reason, they took the casserole out, but they didn't take a temperature reading until 15 minutes later, and then 10 minutes after that. So that's technically 25 minutes. It's the 25-minute mark. So the data points they've given us are not the initial value. They gave us the temperature at the 15-minute mark, and it was 200. And then they gave us the temperature at the 25-minute mark, and that was 14483. Here's the deal, though. We can shift these data points around. We can just sort of rewind time by 15 minutes and just act like this is our initial value. What if I just subtracted 15 and said, hey, you know what? You can just be the initial temp. And that means you getting subtracted by 15 would be the 10-minute mark from there. So 44.83. The deal is by shifting this over, I'm not changing my decay constant. The K value that I get from these 2 points in red is the same as the K value that I would get from these 2 points in blue. So we can do this, it's fine. So that's what we're gonna do. By the way, the rest of the problem is exactly like any other problem now, basically. So if you wanted to tune out, you certainly may, but hopefully you've gotten the help you needed. Let's find that decay constant. Paste, here's my dumb equation, shrink. All right, so we just said that we are gonna treat this point like it's our sort of data point after the initial value. So the 144.83 is our T of T. The ambient temperature is the 75 plus. The initial temperature is the 200, which if you subtract 75 from that leaves you with $1.25. E to the negative K, that's our unknown. The time was 10 minutes. So here we are at the same old place we've always been. I don't know why they had to give us 144.83. Seems like a bit of a jerk move, but that's math for you. 144.83. We're going to subtract 75 from that, bonk. We're going to divide that by 125, bonk. I'm getting a decimal. If I convert it to a fraction, it literally can't be converted to a fraction. Yes, it can. It would be too large to express as a fraction. So I guess we just have to use the decimal. It is 55864 exactly. So we're not in danger of having rounded off. So using this decimal is fine because it's not a rounded off decimal. So it will be just as accurate as if we could have expressed this as a fraction. So we're fine. This equals e to the negative k times 10. You're taking the ln of both sides. that'll give you just the exponent, negative 10k. So you'll take a negative a tenth of that. That'll be k. That means k will be approximately something. It'll be 0.0582. Now guess what? This is a rounded off decimal. This one does go on and on and on and on and on forever. So you can enter this into the quiz, but you darn well better use this expression when it comes time to write your equation. So now they're asking us, what was the temperature of the casserole when it was removed from the oven? Well, I don't know. Don't trick yourself into thinking it was 200 degrees. It wasn't. That's our redefined time zero. That's actually the temperature at 15 minutes, right? So that's fine though. We can still write our model. We can even still continue treating the 200 as the initial value. And so when we solve, we'll get some time before time zero. So what that means is we'll get a time that is negative, and that's fine. Negative times actually do make sense in math class. It just means that it's some time prior to our kind of arbitrarily defined zero time, right? It's not like we're literally going back in time. If you define time zero to be whatever, 3 o'clock, then negative 10 just means 2:50. It means 10 minutes before 3. So that's the second sort of little trick to this, is just because we sort of slid our points around in time, we're going to end up with a negative t value for our answer, but that's okay because we know how to handle it. We know how we've defined our variables. So did they give us an actual time attached to when this thing was taken out? No. So in the cadaver problem, the murder problem, the crime scene investigation problem, you actually have a time. Like the crime scene investigator comes upon the scene at, I think it's 9:30 p.m. or some junk. So when you solve in that problem for the time to be 4 hours, if memory serves, 4 hours and 6 minutes, I believe that's right. They don't want to know just the time. They want to know, like, what does the clock say when this dude was murdered? So you just subtract that. You'd backtrack to 5:24. So I think it's 4 hours, 4 minutes then, because I'm pretty sure I remember it being 5:26. But that time, when you solve for that time, it's negative. And all that means is go backwards on the clock, subtract that amount of time from the current time. And then we could find that the time of death was 5 hours and 26 minutes. I'm not doing that problem because this is already a pretty long video. But you can learn from the casserole problem. You can go back and try the crime scene investigation problem if you want to. These are the answers. I'm 99.9% certain that I have these numbers right. Okay. So anyway, back to the task at hand. We have to write our model. Our model is going to be temperature as time goes by equals the ambient? Yeah, the ambient. Okay. The ambient being 75. Plus the difference in the two temps, which is the 125, times e to the k, which we now know to be a tenth, times the ln of 0.55864 times t. All right, let's do this one last time. So t of t is equal to 75 plus the coefficient of 125 on, we're pulling this out, so our base will change. Our exponent will be t over 10. That's the 1/10, and the t sorted. E to the ln of whatever is whatever. So our base is going to be that decimal this time, 55864. But there's our model. So it says what was the temperature of the casserole when it was removed from the oven? That should say oven. What a typo. All right, this is a little different because they're asking you to find the temp. We haven't really had that problem before. So you know T, and you have to figure out this temp. Well, I know T. Do you know T? You should know T. We got to go back to our redefined variables. What's our temp? Our temp would be, well, we are backtracking everything by 15 minutes, right? So the time that it came out of the oven would have been 15 minutes prior to this time. So that means it's a time of negative 15. So we just have to know to substitute in negative 15 and get an answer. So we want to find T of negative 15. That will give us our initial temp. 75 plus $1.25 times 0.0. Oh, I screwed that up, right? Certainly did. I stuck a 4 on it. What is this? Oh, it's from here. Okay, so I didn't screw anything up. Yeah, no, I didn't. Okay, don't look at that. Never look at that. Erase. So it is 0.55864 to the power of negative 15 tenths, aka just 3 halves. You could dump this whole mess into your calculator to see what it is. I'm gonna do that. So this will be approximately, all right, 75 plus 125 times 0.55864 to the power of, parentheses, so we don't have any unforeseen consequences, negative 15 over 10. I'm getting 347.372, actually 373, because I'm getting 3725451 degrees Fahrenheit. I think we're in Fahrenheit, aren't we? Yeah. You don't want to stand in a 75 degrees Celsius kitchen. That would be a smidgen hot. All right, there you go. That's the initial temp. We know that now. Write an equation using Newton's law of cooling to represent the problem situation. Well, I already wrote one. What was the temperature of the casserole when it was removed from the oven? How were we supposed to do this? We had to write an equation already. I think what they're saying now is, hey, why don't you go ahead now and rewrite your equation using this new initial time? But I don't wanna do that. I'm not gonna. The equation I have is great. I'm gonna stick with it. Write an equation using Newton's law of cooling to represent the problem situation. Done. It's up here. There's nothing wrong with this equation right here. As long as you remember that this does not contain the correct initial time. Everything here has been shifted 15 minutes backward in time. Yeah, okay. So how long from the time the casserole was taken out of the oven does it take to cool to 100 degrees? You guys know the drill. You're gonna plug in 100 for T of T. So 100 equals 75 plus 125. 0.55864 to the power of time over 10. All right. Subtract, get 25, divide by 125, get 1/5. We're already using decimals anyway, so just make it 0.2. That's exact anyway. And that equals 0.55864 to the power of T over 10. You're taking logs of both sides now. You could take the log with a base of 0.55864 if you want to, but if your calculator can't handle that anyway, you may as well just be taking the ln of both sides. You get ln of 0.2 equals, you're going to pull out your power, ln of 0.55864. Now you're dividing by that, so you get the ln of 0.2 over the ln of 0.55864. That equals T over 10, so multiply by 10, essentially just putting it up there. Hey, look, it's what we would have gotten from change of base formula anyway. We would have had 10 times log base 0.55864 of 0.2. If you have a calculator that can't do these logs anyway, then you may as well just take ln of both sides all the time. And then you'll basically have the change of base formula built right into your algebra anyway. You're going to land directly on the expression that you need to put in your calculator. So it's kind of convenient. Speaking of putting something into your calculator, let's do this math. I'm actually going to do the math. Oh, I can't do the math alpha math thing. I am one of you that needs the ln. Okay, fine. 10 ln of 0.2 is some stuff divided by ln of 0.55864 is something else. 27. $642, let's say. All right, that means I have the order pair 27.642, comma, 100 degrees. But wait, this ordered pair represents that shift that we did before, remember? So anything that comes out of this equation needs to be shifted back to normal time, meaning you need to add 15 minutes back on. So if you gave me this as your answer, you would be super wrong. We need to take this and shift it ahead in time again by 15 minutes. So 15 added onto this is 43.642 minutes. And is that what we want? How long from the time the casserole was taken out of the oven? Yeah. So giving your answer just in minutes is fine. Again, I'm never fully confident in my answer. So let's see what Butler said. Cheryl. 42.667. No way, Butler. Oh no. Who could be right? Who could be wrong? I'm going to say maybe Butler rounded off. Maybe I'm right. So she did change her equation around. She's got some weird 300 going on. I don't like it. 58225, 58225. So what'd you do, Butler? It looks like she's showing this dot, dot, dot means she used the entire value of it. Yeah, she's wrong though. Okay, I shouldn't care. It's 43. What happened with her, I think, is she probably did the whole second answer thing in her calculator to just use the previous answer. But your calculator literally only remembers these values. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 characters worth. Oh, 10, because it remembers that. I think that's right. I believe your calculator will only store 10. So there are some values out here that she has lost. And so she has lost a bit of precision. So she is off by a full minute. Like I told you guys, that small loss of precision can mean that you're off by like an entire minute, which is kind of a big deal. So I'm going to go out on a limb and say that my answer is better because I don't have any rounded off stuff. I use the entire values everywhere. Right? Didn't I? Yeah, because I used this log expression. So I was able to get away with using exactly this where I haven't lost anything. She used this where she did lose a smidge. She lost a tiny bit, but that did manifest itself as the loss of an entire minute. I like my answer. I feel good about it. I stand by it. By the way, we're talking about how long it takes a casserole to cool down. So I'm pretty sure it's not a life or death situation. Doesn't really matter if she's getting 42 and I'm getting 43. Okay, I'm done. There's a Walt Wisdom time tomorrow. God, I hope none of you are watching this video. It's 11:15 p.m. right now. If you guys are actually watching this at like midnight, that's not so good. But I'll be available tomorrow. Want wisdom time? Come find me. I'm happy to help you if you need it. Adios.